Okay. Yeah, we're playing now, yeah? Okay. So let's look at this question. Let's look at this question. Now, how do you approach this question? Yes? Exactly. Now, what is my f of x here? Now, what is the solution to this equation? What is x has a solution? It means that this function achieves the value 0, right? Do you agree? So let f be x cubed minus 4x plus 1, minus what is that? Minus 13x squared plus 1. F, is that continuous on 0, 1? Why is that continuous on 0, 1? Because f is a polynomial. So f, since f is a polynomial. Great. Now what is f of 0 in that case? Ah, shoot, wait, this one. What is f of 0? 1. F of 0 is 1. And what is f of 1? It's 1 minus 11, right? So it's 1 minus 13 plus 1. Is that it? Which is minus 11. Now f of 0, is it positive or negative? Positive. F of 1 is positive or negative? Negative. So does 0 lie between f of 0 and f of 1? 0 lies between f of 0 lies between f of 0 and f of 1, or f of 1 and f of 0. I mean, I'm not putting inequalities here. I'm not implying one is smaller than the other, just like there are different signs. What can I say by the intermediate value theorem? By the intermediate value theorem, by the IVT, f of x, or there exists a t in 0, 1, such that f of t is equal to 0. Okay? Yes?
Can you use the brackets with everything open?
No, f should be continuous on the whole interval, exactly. Okay? Yeah? Would you please raise your voice?
You also take the binder function as continuous for you.
Exactly, yeah. If it's not continuous, does it work? So try, for example, a function that is not continuous. Okay? Does it take any value here? No. Okay? So you should really specify continuous on the closed interval. Okay? Now, if there is a number f of t is equal to 0, what does it mean? It means that the equation has a solution, right or no? Okay? Are we good? Then the equation has a solution in 0, 1. Right? You know that neither 0 nor 1 is a solution, right? Because you plug in f of 0 and f of 1. So the solution will lie in the open interval. Yes? Oh, if I tell you, show that the equation x squared minus 3x squared plus 1 is equal to, let's say, minus 5, you also can repeat the same argument, right? Because 1 is bigger than minus 5, and minus 11 is smaller than minus 5. Is that clear? Yeah? Yes? It's a polynomial. A polynomial is continuous. Yeah, we saw that here. A polynomial is continuous. Yes? Would you please raise your voice? Yeah.
Sorry?
Yeah, please. You can speak higher.
Sure. So the intermediate value theorem
Yep.
doesn't tell you the solution, it just tells you that there is a solution.
Exactly. It says that there exists at least one. It doesn't tell you how many of them there are, but it tells you that there exists at least one. Yeah? Yeah?
I think someone asked this earlier, but I wasn't able to hear it. Why is, interval not correct?
Why is? Here or here?
In the middle.
Here. Sure. I mean, here you mean, right?
Sorry.
You could put the brackets here. If you put the brackets here, it's correct. But you know that f of 0 is not 0, and f of 1 is not 0. So you could just eliminate it. Yeah. Any question? Yeah. Yeah. So if I tell you, show that the equation f of x is equal to 5 has a solution, would the same argument work? F of x equal minus 5 has a solution. F of 0 is 1, which is strictly greater than minus 5. F of 1 is minus 11, which is strictly smaller than minus 5. So the equation f of x equal minus 5 has a solution. Okay? So do you do one more or not? Yeah, let's do one more. So, let's do an example. Let f of x or show that there exists I don't know. Let's see. A solution to the equation f of x. Sorry. Let's see. Arc tan x plus x is equal to 1. Are we good with tan? Yeah. Show that there exists a solution to the equation arc tan x plus x is equal to 1. Do we all know the inverse trig functions? Okay, so for the inverse trig functions, if you don't know them, I invite you to read the first chapter of the book. They're very important. They will be very important, and it's big class knowledge, so you must know them. Great. Now, how do we proceed here? Yeah. Sure. What is my function, first of all? I mean, there are many ways you can proceed. So if I put my f of x equal arc tan x plus x, what value I'm interested in? F of x is equal to what? 1. Now if I put everything on one side, and I have arc tan x plus x minus 1 is equal to 0, and I let my f of x be arc tan x plus x minus 1, what value of this function am I interested in? F is 0, right? You see that? You guys see that? So I can put everything on the same side. Right? And let my f of x be arc tan x plus x minus 1. You agree or not? Then what happens? is that continuous on R? Is f continuous on R? First of all, what is the domain of f? Arctan x is defined for any x or not? Yeah, arctan x is defined for all x in R. Is x minus 1 defined for all x in R? Yeah, so what is the domain of f? F is defined on the entire real number. Now, is f of x equal arctan x plus x minus 1 continuous everywhere on R? F is continuous everywhere, do you agree? Yeah? You all agree with this or not? Yeah? F is continuous on R. Since x arctan x and x minus 1 are continuous on R. Now, what can I say? I need to show that this equation has a solution. Did I give you an interval to check? No. So technically, you have to give me the interval. Right? You have to test our interval. Now, what is enough? Suppose, like, someone gives me a number, say a, such that f of a is negative. And someone else gives me a number, such as b, such that f of b is positive. Do I achieve my goal or not? Everybody? Do we see that? Because someone gave me f of a as a such that f of a is negative, and b such that f of b is positive. This means that my function f will achieve the value 0. Right? So if it achieves the value 0, then I have a solution to this equation, which is equivalent to this equation, by just rearranging. Okay, now what do you suggest? What numbers could I plug in? What's the easiest number to plug in here? Yeah? 0. What is f of 0? What is f of 0? Arctan of 0 plus 0 minus 1, what is that? Minus 1, right? We agree or not? Everybody, what is arctan of 0? 0, right? F of 0 is minus 1. What's another number? 1. What's f of 1? Let's look at f of 1. F of 1 is arctan 1 plus 1 minus 1. So this is just arctan 1. Or is arctan 1 positive or negative? I mean, you know it, right? What's arctan 1? 5 or 4, right? Yeah? You know that? No? You don't know that? I mean, you don't need to know the exact value, you just need to know it's positive, right? Arctan 1 is positive. It's in fact equal to 5 or 4. Now, by the IVG, what can I say? I can say that since f is continuous on 0, 1, by the IVG, there exists C in 0, 1 such that f of C is equal to 0, and hence, it's good, that's very good, and hence there exists a solution to the equation arctan x plus x is equal to 1. Okay? It's a bit hard to do this on your notebook, but okay? Great. So usually on the midterm or on the final you will have a question on this. So like if you like get a question like that, please don't mess it up. It's easy points. You just have to justify correctly and have the correct approach. Great. questions? Yes, sir.
There was,
You can remember?
can't remember.
Okay. Questions? Yeah?
Concerning,
Yeah, okay, sure. Yeah. Go ahead.
concerning grounds where, for instance, there is a value, at f of a, that is somewhere in the, I guess, consider a sine function where you're taking minus pi over 2 and pi over 2.
Okay.
So that there will be values within the, function that be
Yep.
lower than OP.
Sure.
Does the intermediate value here account for that, or?
Yes. Yes. If it's continuous. Yes. Oh, you remember your question? So I'll take her question and then go. Yes.
We always have to.
Guys! Someone is asking question. Yeah.
Does we always have to calculate it to equal 0, or was that just?
No, I mean, if you work with arctan x plus x, it should be equal 1. You write f of 0 is 0, f of 1 is pi over 4 plus 1, right? It's pi over 4 plus 1 is bigger than 1, and f of 0 is less than 1, right? But it's better to, I prefer to bring everything on the other side, okay? Yes.
I don't understand how you look at arctan 1 plus 1 and just know it's continuous.
Arctan x, you mean, arctan x. Arctan x is an inverse trig function, right? Inverse trig functions are continuous on their domains. We saw this theorem last time, right? Did we see that? Yeah. Someone had a question here. Who had a question? You? Someone did? Yeah, no. You had a question. Yeah? Oh, just by law. I tried f of 0 and I tried f of 1. There are different signs.
So we can just, all the functions, we can just plug in F0 and F1.
Well, if there are different signs, it will work. If there are not of different signs, it won't work. Okay? Yeah? Yeah?
Will there ever be a situation where you have to choose a very large interval, like a value like negative 100?
Yeah? Yeah, could be. Okay, great. Yes, sir.
Just so for the intervals,
Guys, someone's asking a question, please. Yes.
if we're choosing the intervals out of the block, is there no set way of choosing the correct interval, or?
If there is,
So, because you just said you chose 0 and 1 out of block, if that doesn't work, and then you just
you have to do another interval.
just keep choosing random numbers?
No, I mean, you have to make a nice guess, right? You have to know that if x is positive, say, arctan x plus x is positive,
Yeah.
right? So you know that for positive values of x, arctan x plus x is positive. And then you want it to exceed a bit 1, right? So, okay, you have to make a guess, okay? Yeah.
Can we also use this theorem to give two graphs, if two different functions meet our point on the graph?
Pardon me?
Can we use this theorem to give two different functions meet our point on the graph?
Yeah, exactly, because you can take the difference of two functions, right? If you have the difference of two functions equal to 0, and the functions must be continuous. Yep. Yeah, last question, yeah?
Do you always have to choose like the lowest value arc sine or arc?
Do I have to use
You
this?
always have to choose like the lowest value.
No. So you could put here arctan of 1700. That will work, okay?
For arctan 0 is
Arctan of 0 is 0.
okay, for
Beg your pardon? Sorry?
can't it also be pi?
Arctan of 5. Well,
No, arctan like on the
no, so arctan is defined on minus pi over 2, sorry, so the range of arctan belongs to minus pi by 2, pi by 2. Right? Okay? Great. Right, this is, please revisit this. Okay, now, let's move on. Yes, sir.
So if we had something like a time function, then we would have to choose the value before the asymptote.
Well, I mean, I'll be clear then. Yeah, exactly. You have to choose on an interval where it's continuous. Yeah. Okay, great. Now there is something where, well, let's not do that. I mean, you know, I'll just talk a bit about the types of discontinuities, and then you know. I think explain the different nuance that we are using and the book is not using. Okay, so the book mentions, for example, that 1 over x is discontinuous at 0. Okay, now in this course we will not be making a statement like that. To talk about continuity and discontinuity at a point, the function has to be defined at that point. Okay, is 1 over x defined at 0? No. Okay, so I cannot talk about the continuity and discontinuity of a function not defined. I'll just mention some discontinuities. A jump discontinuity is, for example, when you have something like that. Okay, what is this is 1, this is 2, and this is 1. What is f of 0? 2. What is the limit as x is approaching 0 plus 2? 0 minus 1. So this is a jump discontinuity, right? You're just jumping. Okay, you guys see that? Now there's another type of discontinuity called an infinite discontinuity. Whenever this is called an infinite discontinuity. And what as well? You see why it's an infinite discontinuity? So f of 0, let's say, is 1, but on the right, the left, the x is approaching 0 minus, what is that? F of x goes to infinity. So you have an infinite discontinuity, and then you have something called the removable discontinuity. So let's say f of 2 is 5, but the limit on either side is the same, right? So that's what we call the removable discontinuity. And they're not very tough to see. And now we'll move on to more important stuff. Limit at infinity. By the way, I see that not many of you are practicing the questions, the odd numbered exercise. I mean, I've seen few of you who came and see me during office hours and after class. But I can tell you that the first web work is due in October, someday in October. So it's pretty far. It's not like soon. But what I want you guys to do is try to practice. Because if you're counting only on the web works, it's not going to work. Okay? So please practice every week. I'm just asking you 2 to 3 hours every week. And you will be, instead of homework, instead of labs, you know, you have this practice. Practice 2 to 3 hours every week, and I can guarantee you, well, even more than 3 hours. But yes, the removable one. So if you put this value here, would the function be continuous? Okay. Okay. So please do your practice questions. Just I will. It's on there. Okay. Are we finding them difficult or not? For those who tried, are we finding the suggested questions difficult? No? They're good? They're difficult? They should be. I mean, they should not be easy. If you're struggling, please come and see me. Okay? Yeah? These are not challenge questions.
They're not challenge questions.
These are extra. These are extra. I mean, they look, guys. Someone asked me a question, please. So these look exactly like.
Yeah, sorry. I was confusing with my. They're not challenge.
Both of it.
They're just both of them.
Yeah. I mean, the others I give you a solution to.
There's nothing else you're trying to do.
No, only that. If you do only that, I'm happy. Okay? Yeah. Yes, there's a hole here, and the value of the function is somewhere else. Now notice if you set the value of the function to be here, it will be continuous. Okay? Great. Let's go for limit at infinity. Okay. Limit at infinity. Okay, so thus far we have been interested to look at the limit as x approaches a number a, for example, right? Yeah? Now, we did not look at what happens for very large values of x, right? We said like if x is close to 1, what happens to f? Now we're going to be interested what happens for very large values of x. Okay, so let f be defined on an interval of the form. Let's say, I don't know, m infinity, let's say m here. We say that limit as x is going to infinity of f of x is equal to L if f of x can be made arbitrarily goes to L by taking x sufficiently large positive. Okay? Let me see if that's the definition we have in the book. Large positive because I'm not looking about. Okay? Now, basically, let's look at something. Maybe I should give an example. Limit as x approaches infinity to 1 over x. Now, if x is approaching infinity, where do you expect 1 over x to go? X is a very positive. X is a very large positive number. What do you expect 1 over x to be? Everybody. Does that make sense? Now, if I want 1 over x to be smaller than 1, if I want 1 over x to be smaller than 1, well, to be smaller than, I don't know, give me a big number. Let's say 10 to the 12. Okay? Can I make 1 over x smaller than 10 to the minus 12 series? Can I make that? How do I choose my x? X to be bigger than 10 over 12, right? You agree with this or not? So I can make 1 over x sufficiently close to 0 by requiring x to be bigger than 10 over 12. Okay? Is that clear? That's what definition means. We're going to see more of that on Friday by using epsilons and deltas. Now, let's look at one more example. Well, if I give x minus infinity 1 over x, what is that equal to? Also 0, right? Very good. Now, of course, all the other definitions can be given in the same way. Let's give a few limits. the limit as x approaches infinity of, let's say, I don't know, x plus 1, for example, or x squared plus 1. What is that equal to? Everybody? Infinity. Okay, so I write plus infinity. You can omit the plus if it's positive. I'm just used to writing plus infinity, okay? Great. Now, let's look at another indeterminate form, which is the infinity over infinity. Thus far we have seen one indeterminate form. What is that? 0 over 0. Now infinity over infinity is also an indeterminate form. Let's look at a nice example. I'll write here. The limit as x approaches infinity of x over x. What is that? So where does x go to when x approaches x goes to infinity? Infinity. Where does x go to when x approaches infinity? Infinity. But where does this quotient go to? This quotient is identically equal to 1 as long as x is non-zero. You agree? Now if x is approaching infinity, then x is very big. So this is just 1, which is 1. Now, how can you make a change to still remain in an infinity over infinity case, but I get an answer of 10, say? Yeah? Of 10x over x. So what is the limit as x approaches infinity of 10x over x? 10, right? What is that? 10. Now both cases, if I plugged in the limit law, if I did the limit laws, what do I get? I get infinity over infinity. So infinity over infinity is an indeterminate form. Okay, is it clear? So whenever you have an infinity over infinity, it means you have to work it out. Okay, and do something. Just like 0 over 0. When you had a 0 over 0, what did we do? We had to do some transformations or play with the expression to be able to evaluate it. Right? Same thing for infinity over infinity. Let's give an example. Of course, limit laws hold and okay, the regular limit laws provided the limit exists. Okay? Right, you can cancel, simplify. Let's start by something nice. Limit x goes to infinity. Who wants to send me their favorite number? Yes? 67, okay. Okay, someone else? Yeah? 37. 67 is a prime number, 37 is a prime, 67 is a prime number, right? Yes, 67 is a prime number, no? Yeah, 67 and 37 both are prime. Yeah, that's good. Okay. Wait, is it? 67 is a prime number. Yeah. You know to test if a number is prime, if a small number is prime? Anyways, let's see. Yeah, okay. Great. Anyone, their favorite number? In the back, yeah, the two in the back? 45 and? Yeah, you? No, you said 45.
I said 60.
Oh, you said 4 and she said 45?
29.
29. Okay, so the 4 proves the prime number pattern. Okay, first of all, what do I try to do? I try to, yes sir. You want to give your number? Oh, I thought you wanted to give a number. Too late now, yes. Yes, but let's try to yes. Very good, so, great. Now let's look at this expression. The numerator, where does it go to as x goes to infinity? Infinity, right? You have a linear function, and if x is very large, it will be very large, right? With a positive, because the slope is positive. You see that? Okay, the bottom, what will happen to the bottom? It's also infinity. You agree? So I have an infinity over infinity, which is an indeterminate form. Now, for now, I have to do something. Okay? Now, usually the trick is that you want to look at the term that dominates. The term that dictates the behavior of your numerator and of your denominator. What is the term on top that dominates the numerator? Is it the 37 or the x? X. So let me take an x out. If I take an x out, what do I get? What do I have to do? 67 plus 37 over x. Great. On the denominator, what happens here? I can take an x out. What do I get? I get 4 plus 29 over x. Did I get rid of my indeterminate form, or the x's are still here? The x's are? Everybody. Still there. So what do I have to do? I can. Everyone, what can I do? I can cancel them. What do we get? 67 plus 37 over x. 4 plus 29 over x. What do I get here? Now look at the top. 37 over x, where will it go to? If x is very large. So the top, where will the top go to? 67. The bottom, where will it go to? 4. So what is my answer here? 67 over. Are we good? Any questions on this? So you know that I know that you've used some tricks in high school. You know, look at the largest powers and divide them. And I don't know what. I don't want to see any of that. You have to work out all. You have to show all of these steps. Okay? Let's do one more. Let's go a bit harder. We still have 2 minutes. Limit as x approaches infinity. Who wants to give their favorite number? Yeah? 13, okay. Prime numbers. Okay? Yeah? 14. Let's look at this term. I have a 13x squared plus 14x plus 1 over 6x cubed plus 17. I try to plug in, what do I get? The top, where does the top go to? Infinity. The bottom, where does the bottom go to? So what do I get when I plug in? Infinity over infinity. Is that good? No. So I have to evaluate the limit. Now, what do you expect the dominating power to be? 13x squared plus 14x plus 1. What do you expect the power, the biggest power? What do you expect to say that I am the one who leads? As x goes to infinity. It's the x squared, right? You see that? Everybody. So let me take an x squared down to the top. X squared, what am I left with? 13 plus 14 over x plus 1 over x squared. Great. Here, what do you expect the biggest term to be? X cubed, right? I mean, the 17 doesn't do much. 6 plus 17 over x cubed. Now, what can you do with the x squared over x cubed? You can simplify this fraction by canceling out an x squared from each of these terms, right? So what do you get? You get 1 over x times what? Well, not 1 over x. 13 plus what do you have? 14 over x plus 1 over x squared. Okay, x and what do you get here? 6 plus 17 over x cubed. Is that what you get? Yeah? Is that right correctly? Great. Now let's look at the top. Where does the top go to? 13. The bottom, where does, well, the bottom consists of two things. This one, where will it go to? 6. And this one, where will it go to? Infinity. So I have a 13 over 6 times infinity. What is that equal to? 0. Okay? Is that clear? Yeah. Okay. Thank you very much, and see you on Friday.